Hello, my name is Julian, and today I'll be explaining the SAR ADC, or Successive Approximation Register, used as an analog to digital converter. I'll first and foremost go over the clock, as it's what I've physically built so far. Then I'll go over the entire build as an overview through a SPICE diagram I sketched up earlier today. I hope to leave you with a greater understanding of this particular ADC by giving you the why rather than just some output. So, as you've been seeing on screen for us a little bit, my clock is functional and it's producing roughly 10 kilohertz. However, you might be thinking to yourself, why does it give 10 kilohertz, and also why do we even need a clock? What is the SAR ADC? Well, we'll get to the purpose in a moment, but first I'll break down inverter-based RC oscillators. We'll be using a simplified equation for demonstration, but here we have frequency equals 1 over 2 times resistance over capacitance. And when we sub in our used 510 ohms and 0.0 microfarads, we'll get roughly 10 kilohertz. And now, to understand where this equation came from, we need to first realize that this equation isn't actually true at all. The true charging law is given as V of t equals VCC times 1 minus e to the negative t over RC. And if we assume the circuit switches when the capacitance reaches some fraction of k over VCC, we can rearrange to get t equals negative RC times the natural logarithm of 1 minus k, which is the time for one charge or the time for one discharge. And for inverters, and most other oscillating-based circuits for that matter, when they're applied in real life, the capacitor moves between a third and 2/3 of VCC, which is set by the resistors. And therefore, we can find out how long it takes to go between these by setting V of t to 2 over thirds of VCC, and plugging that back into the equation, we'll get t equals minus r times c times the natural logarithm of 1 over 3. And doing the same for a third of VCC, which is the other part, we'll get the natural logarithm of 2 over 3. So if we want to find out the time between these two intervals, we just subtract t 2 over 3 by t 1 over 3 to get the amount of time to charge as RC time, or as the equation RC times the natural logarithm of 2, and since we need a charge and discharge, which takes the same amount of time, we multiply this by 2 to get 1.386 RC equals the total period. And now since we know the frequency equation, which is 1 over period, we can do 1 over 1.36 RC. And this looks awfully familiar, as we just saw 1 over 2 RC, and you'd be right, these are the same equations. But we as engineers say 1.36 is roughly equal to 2, given the uncertainties present in real life. So we just say 1 over 2 RC. Well, now that you understand the clock, let's move on to the why, the actual SAR ADC. On screen you're seeing my LTspice diagram of Yamada's SAR ADC. You'll have to excuse this atrocious circuit diagram. This tool's a pain to use and I'm quite tired. Well, anyway, back on topic. What you're seeing on the top left is a 10 kilohertz clock signal, which I've made as an ideal frequency, which is just these numbers. And this is instead of our oscillating circuit, because that's incredibly difficult to make in this program for whatever reason. Anyways, the clock drives our sample and hold, amongst other things, but I'll first talk about the sample and hold. The sample and hold is what's our analog voltage that we're converting to a digital signal. At the moment it is set to 5 volts, but I'll change it later for testing. And what the sample and hold does is, because the clock clocks once per conversion, it'll output a stable voltage for however long the ADC needs. And this voltage will be compared with this mysterious other input, which I'll talk about in a second. But the output goes to an inverter, because the only comparator this tool has an inverted output, which is very strange. But this goes to the inputs of our flip-flops, of which have outputs that are our digital outputs for our circuit. anyways, the input it's comparing it against is this DAC, which has inputs from the aforementioned flip-flops through an AND gate, which we'll talk about what it's ANDing with in a second. But basically, this DAC is asking the question, or not really the DAC, the comparator is asking the question, is the input voltage higher than the DAC voltage right now? And the DAC voltage is basically just a guess, or not really a guess, it just takes the voltage, the pre-voltage, and then it adds the next voltage. So it's an estimated guess onto what the analog input is. This guess is generated based on the current bits, which I just said. So if our guess is too big, well, we know that bit must be a 0, since anything with that bit will be too big. Then we guess again. Oh, this time it's smaller. That means that this bit can be set. So, to store these, well, you guessed it, it gets stored into the flip-flops from this output. And so you may be thinking to yourself, if the comparator output is all wired to the same thing, I mean, look, the D inputs are all the same, won't they just receive the same value and be the same thing? Well, let me tell you, these flip-flops are not being updated at the same time. If you look here, the shift register, there's a makeshift shift register. We don't get shift registers on this platform. We only get flip-flops, so I had to make my own. But this shift register thing will be our little clock signal, which will update at distinct times, 3 distinct times for each of the samplings, or not samplings, sorry, for each of the comparisons. And these will all be reset through a reset flip-flop. That's what the fourth one is. This just gives us non-overlapping resets just for proper shift register functionality. And anyways, this is fed to the flip-flops, and voila, you're storing what you're finding. However, you may have a new question. How do these flip-flops even get an initial testing value? These flip-flops, since I did mention that they'd be testing something initially. Well, we don't really know. Well, the shift register, as I just discussed, can do another handy thing, which is to preload the flip-flops in sequence to test binary weighted values. You can see it tracks the MSB first. Sorry, my wiring is really hard to follow, but you can see this it goes from the clear, which is from the clocking, but yeah, sorry, my wiring is really messy, it's really hard to follow, but you get the general idea. So let's actually probe some inputs. So we have 5 volts on right now. Let's simulate. Well, it's 5 volts. It's referencing against 5 volts. If you had to take a guess, what will it give? High, high, high. These are just the waveforms from when it's testing. This isn't very interesting, so let's try actually interesting voltage, like 3 volts. So, put in 3, simulate, run. So, let's step over. Let's go here. Well, we know, or I guess this isn't a good place to start. Let me just rerun that. So, at the very first step, at A4, the DAC outputs a 2.5 volts. 2.5 volts. It's a little hard to see when, but yeah, first output's 2.5 volts, which is fed into this. Since 3 volts is greater than 2.5 volts, the comparator sends a high into the register A4, which then latches a high. Or I guess a 1. Then the sequencer pulses the next gate, and then the DAC adds 1.25 volts to the previous 2.5 volts, which tests 3.75 volts. Since 3 volts is less than 3.75 volts, this will be a low. And again, the comparator sends a low, and then register A3 latches 0. The sequencer A2 pulls its final gate, and the DAC tests 2.5 volts plus 0.625 volts, which is 3.125 volts. And again, since 3 volts is less than, this will also be a 0. Well, this video is getting really long, and I've wasted enough of your time, so thanks for listening. This was a pain to make, so I hope you learned something.